Today, I will talk about non-contractible periodic orbits in Hamiltonian dynamics on tori. Namely, I will show that a theorem of Guerre, which she talked today, is also true for tori. And tori is not a toroidal or toroidal monotone. And to state the main result, let me introduce some conventions and notation. Today, let M omega be a connected, closed, symbiotic manifold and alpha be a Floer class of free loops. In Guerre's term, this is Hamiltonian of M. And let H be a one periodic time-dependent Hamiltonian function. On M. Then we have the Hamiltonian vector field denoted by XH. And Hamiltonian isotopy denoted by phi HT. And if I write phi h, this stands for the time map of this Hamiltonian isotopy and called Hamiltonian diffeomorphism. And define the set of k-periodic orbits of H representing alpha by this notation. Then now I can state my main theorem. Let H be a time-dependent Hamiltonian function on the torus, 2n dimensional torus. Here we equip with the standard symplectic form. And if phi h has an isolated periodic orbit x with homotopy class alpha and the local Floer homology of x, which is defined by Ginsburg, this morning does not vanish and satisfy some conditions. Satisfying some conditions. One is the homotopy class of X is non-trivial. And second is the number of one periodic orbits of H representing this alpha, and the number of this set is finite. Then the same argument with dual holds, namely for every sufficiently large prime P, phi H phi H has a simple periodic orbit. With in the homotopy class alpha p and with period p or p prime. This p prime is the next prime greater than p. As you realized, this theorem was motivated by Ginsburg-Curé's work, so I must introduce their work, namely this theorem also holds for a toroidal closed symplectic manifolds with a toroidal symplectic manifold type forms. She proved today and concerning to hyperbolic groups condition was given in Orita. Moreover, also holds for toroidal monotone symplectic manifolds. Under some assumption concerning to a kind of or a characteristic. This is also work by Ginsburg-Curer. However, the standard symplectic torus is not a toroidal or toroidal monotone. In a toroidal case, the axiom functional is independent of the choice of the recapping. So we can use ordinary Fourier theory. And in toroidal monotone case, we should choose recapping, but they use augmented action filtration. By using augmented action filtration, they could avoid to use the Floer-Novikov homology. But in our case, we should use the Floer-Novikov homology. In fact, the theorem holds in more general case setting. Two states that let me introduce some notions. Denotes by Lm. Define Lm to be the set of free loops. In M, and for free homotopy class of free loops, let L alpha M be the alpha component of Lm. Then the symplectic form omega and the first chunk class C1 define classes omega bar in the first cohomology class of the free loop space. C1 defines a class C bar. Respectively. Because a class in this first homology group can be represented by a linear combination of a map from the torus. Then we define this cohomology class by integrating omega over these maps. Then I introduce the following notion. The symplectic form omega is said to be alpha rational. If this group is discrete in R, namely there exists some real number H alpha, this group is equal to H alpha Z. I introduce this notion. Then there are many examples. At first, if omega is atoidal, then for all alpha, omega is alpha rational. Because if omega is atoidal, this group vanishes, trivial group. So for all alpha, H alpha is equal to 0. Moreover, if the manifold is toroidal monotone, namely the set of integrals of the symplectic form is some lambda times the set of integrals of C1. Then for all alpha, H alpha is lambda times C1 alpha mean. This is the alpha toroidal minimal Chern number, namely the positive generator of subgroup C1 bar So this notion is rather general. And of course, I will mention later the standard simplex structure on the torus is also rational. Now let me show this theorem by assuming that I didn't write the generalized proposition. Let H be a time-dependent Hamiltonian function on a closed symplectic manifold M omega. And if phi H has an isolated periodic orbit X, with homotopy class alpha, and the local Floer homology doesn't vanish. Moreover, we assume 4 conditions. The first one is the homology class of alpha in is not equal to 0 in the first homology modulo torsions. The second condition is some finiteness condition. And the third and fourth conditions are different from main theorem. The third one is omega is alpha rational. And in fact, this third condition is not so restrictive, because every toroidal and toroidal monotone manifolds satisfy this condition. So not so bad, but the fourth condition is rather restrictive. The fourth one is for all k. In fact, for all sufficiently large prime p, the following is satisfied. Namely, this homogeneous condition holds. Then the same conclusion holds. At first, I will explain some examples meeting the requirements of the proposition. The first one is, of course, if an omega is a closed symplectic manifold with a toroidal symplectic form. In this case, 3 is satisfied, and in 4, the both terms are vanishes. So the proof of this case is actually the same with Gale's work. And we have an example as the product one. Omega satisfies 3 and 4, and omega n is a toroidal. This case also satisfies the condition, because if we compute this group, we can separate into 2 terms. And of course, from the toroidal condition, the second term vanishes. So if omega satisfies 2 conditions, then so omega plus omega n does. Yes. And of course, the main result is an example. Yes. Yes. Thank you. Thank you so much. Yeah, yes. Next, I would like to prove the theorem by assuming that the proposition holds. Proof of from proposition to the theorem. At first, let me introduce a notion called primitive. An element E in Z to 2M is said to be primitive if for all positive integer k and for all element except, sorry, I write here M, except E. E is not equal to Kf. And now we consider the standard symplectic torus. And let alpha be a free homotopy class in T in the torus. This is isomorphic to Z2M. Then if alpha is not equal to 0, there exists positive integer. There exists a positive integer H alpha and a primitive vector such that alpha is equal to H alpha times E. And if when alpha is equal to 0, we put H alpha is equal to 0. Under this preparation, I will show the theorem. It is enough to show the following lemma. For all free homotopy class in the torus, we have the following equation. Namely, this group can be computed as explicitly. and this is equal to H alpha Z. Namely, this last equality shows that the standard symplectic structure on the torus satisfies the condition 3. In particular, for all k, for all positive integer k, we have the condition 4. Because alpha k is equal to k h alpha e. So if I prove this lemma, then we can prove the main theorem. So now I will prove this lemma. Yes. Okay. Since the torus is a Lie group, with some multiplication mu, there exists a bilinear map P from the ith homology group times jth homology group here. This time stands for cross product. And from this homology group, we have a homomorphism induced by mu. Namely, the target is homology group of T to M. And P is the composition of these maps. And this P is called the Pontryagin product. This is the crucial property. Then it is known that the Pontryagin ring, namely the associative algebra of homology groups with this product, is the exterior algebra. Here xi, the degree of xi is equal to 1. And let H be a map from the set of free homotopy classes to the first homology group defined by for a free homotopy class alpha, and we choose a free loop representing alpha. For such alpha, x, we define this map by the push forward And here, S1 stands for the fundamental class. Of S1. Now, we wanted to understand the structure of this group, so let us choose an element in this group. Now, every element A in the fundamental group of the free loops space is represented by a map from the torus such that the restriction to the first component represents alpha. And let beta be the free homotopy class of the second restriction. The restriction to the second component. Then every element A can be identified with an element P, H alpha, H beta in the second homology group. P is the Pontryagin product. And now let us denote alpha is equal to A1 blah 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 A2n in Z2n. Then we can compute this group directly. That is this group is the set of integrals of omega without bar over these guys. Here beta is in the set of free homotopy class. And the Pontryagin product is now the exterior product. So this is equal to A1 blah 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 An is equal to alpha, and if we denote beta by B1 blah 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 B2n, we can write down like this. And of course, this can be computed directly. this is equal to this is standard computation, so I omit the details. Then the integral of this form over this vector is equal to this integral. And now here is equal to 1. So we get the desired equality. This lemma, the proof of this lemma shows that the condition 4 holds for any closed symplectic manifold having the Pontryagin product and satisfies this equality. So every Lie group, although every Lie group has this property, but every symplectic compact Lie group is a torus by the old result by Shu. 74, yes. So now I'm looking for some examples satisfying these conditions other than torus. Anyway, the rest of the proof of the theorem is to prove proposition, and I have 15 minutes.
Condition 4.
Yes.
The left-hand side it includes the right-hand side. That's trivial.
Yeah.
The real condition is the left-hand side.
Yes.
In the right.
Yes. Yeah. This is trivial. The problem is here. Yes. Thank you. Now I move to proof of proposition. The proof of proposition mainly relies on the argument by Guel. So I want to explain the reason why the assumption 4 appears mainly. At first, assume that H has no simple p periodic orbit. In alpha p for sufficiently large prime p. Since p is prime, all p periodic orbits in alpha p are the piece iteration of one periodic orbit. As mentioned by Guel. Of one periodic orbits in alpha. Here, we use 2 and 4 sufficient large prime P. And the next claim is crucial. We claim that this equality, and I've not defined this action spectrum. I define briefly. The action spectrum is the critical value, the set of critical values of the action function, and the P1 bar is some lifts of one periodic orbits, and pi is the covering projection whose structure group is and then the action function is defined on this covering space by the formula to define this, we should fix a reference loop Z in alpha. Namely, if this is the reference loop Z, and if this is X in same homotopy class, then we can connect these two orbits pi, and we integrate over this pi omega. And of course, unless we consider the covering space, this is not this action function is not well defined, because now we consider not non-toroidal case. So in general, this action function depends on the choice of the recapping, but now it's okay. And I prove this claim. At first, as mentioned by Mitsumatsu, this direction is trivial because every element in here is P times an element in here. This is trivial. But the opposite side is non-trivial. Let us choose C in the right-hand term. then by our assumption and by the condition 2, there exists some lift of one periodic orbit, y bar, and A in Taiwan L alpha PM such that every element in this set can be represented by P times y bar, the piece iteration of y bar sharp, this is concatenation A. And this can be computed, oh, sorry. Which is, oh, sorry, I made a mistake, crucial mistake. This side is trivial. Sorry, I'm very sorry. Because we have this equality. And the opposite side is non-trivial. I'm sorry. Namely, let us choose C in spectrum of HP alpha P. Then there exists y bar and A in alpha P, such that C equals to this. Then we can compute as this, like this. And by the condition 4, there exists an element B in the fundamental group of alpha component of M, such that the integral of A is equal to P times integrals of B. Then C is equal to P times the action of y bar minus the set of integrals of B. This is equal to and this is in the right hand side. Yes. Thank you. I was confused. Thank you. Yes, thank you. Yes, this is an element in the right hand side. Yes. And the rest of the proof is exactly the same as Gray's work, so I omit. And the crucial point is that equality, namely I draw a picture. This is a periodic orbit in the base space. The piece iterated one. And this is uniterated one periodic orbits in of H. And we lift them to the covering space like this. And this X stands for the action function. From our assumption, every element in base space is derived from one periodic one. Because we assume HP has no simple p periodic orbit. And if I lift them into the covering space, this is piece iteration. And there are some lifts by action, Novikov action. Like this. Then of course, A to the piece acts on this lift, but not every lift can be obtained by this way, because in general, this group is bigger than this group. So some bad action may occur. Which does not obtain by this way. So we need this condition. So I stop here. Thank you so much for your attention.